This presentation on finding confidence intervals for a mean when the standard deviation is unknown is the third part of a series on statistical inference. As in the previous presentations, the instructional design was developed by David Kleinbaum, statistician, and Anna Washington, educator, and the narration was done by David Kleinbaum. For this presentation, we will assume that you already learned from previous study what a confidence interval is in general and how it may be computed for estimating the population mean mu when the standard deviation sigma is known. Since realistically we rarely ever know sigma, it is necessary to determine how to compute a confidence interval for mu when sigma is unknown, which is the subject of this presentation. To find a confidence interval with sigma unknown, we will be utilizing the t-distribution, which will be described and explained in this presentation. As an example of a confidence interval problem, recall the example of measuring the health of residents in low-income housing projects in Angina, North Carolina, which was considered in the previous presentation on confidence intervals for the mean when sigma was known. The measuring index was CMI, the Cornell Medical Index, which comprises a scale from 0 to 100 and gives a summary index of a person's self-perceived health status, where higher scores indicate poorer health. For that example, we considered a random sample, as shown below, of 25 heads of households obtained from the 210 households in a housing project which was 95% black, surrounded by a neighborhood which was 85% white. For this sample of 25, the sample mean of the CMI scores X bar turned out to be 20.84, and the sample standard deviation of CMI scores was 17.53. The question of interest for these data was, based on the sample, what could be concluded about mu, the unknown population mean CMI score of all heads of households in the project, not just the 25 who were randomly sampled. When we previously dealt with this question, we computed a confidence interval, as indicated by the two white dots on the black line located underneath the distribution of the population. We calculated this interval by starting with the sample mean X bar as shown at the bottom. We also took into account the variability of X bar, which required us to consider the hypothetical sampling distribution of X bar, as indicated by the purple curve shown in the middle. In particular, we made the assumption that the standard deviation of X bar was known to be sigma over the square root of n, where sigma was the standard deviation of the entire population of CMI scores. The value of sigma was assumed to be equal to 16, as shown at the top. Such an assumption about sigma being known is difficult to justify, since even if we use previous studies on similar populations to determine a value for sigma, it is always possible that the population of the current study has different variability. Thus, rather than risking inaccurate extrapolation from other studies, it makes sense to consider using a confidence interval which doesn't make the assumption of known sigma, but instead uses the sample standard deviation S to take into account the variability of X bar. We will now describe how to obtain a confidence interval formula for mu assuming sigma is not known and the sample standard deviation is used in its place. We will then return to our specific example about CMI scores to illustrate the method for computing such an interval. Recall that the general formula for finding a 1 minus alpha % confidence interval for mu when sigma is known is given by the expression at the top, namely X bar plus or minus z sub 1 minus alpha over 2 times sigma over the square root of n, where z sub 1 minus alpha over 2 denotes the 1 minus alpha over 2 percentage point of the standard normal distribution. It turns out that the confidence interval for mu when sigma is unknown is given by a similar expression shown here at the bottom. However, when sigma is unknown, we must replace the z percentage point and the value of sigma used in the top formula by two other quantities, which we have left blank for the moment. To explain this change, let us briefly review the process involved in deriving the top formula for known sigma. In order to obtain a confidence interval for mu when sigma is known, we started with a probability statement about a standard normal variable, such as the first expression at the top. We then substituted for z the expression x bar minus mu divided by sigma over the square root of n, as shown in the middle. We then worked with the inequality inside the parentheses so as to get mu at its center, as shown at the bottom. The two limits in this statement describe what we call the confidence interval. For the example shown, a 95% confidence interval for mu has the limits 14.6 and 27.1. The statistic which we had to manipulate to obtain the confidence interval when sigma was known is again pictured at the top. That is, z equal to x bar minus mu divided by sigma over the square root of n. When sigma is unknown, we can derive our confidence interval through a similar process, but we must work with a different statistic as shown at the bottom. The right-hand side of this expression, x bar minus mu divided by s over the square root of n, has a different denominator from that above, since sigma has now been replaced by the sample standard deviation s. Also, we have called this new expression a t-statistic in contrast to the use of z above. Rather than following the standard normal distribution, the probability pattern described by the statistic t equals x bar minus mu divided by s over the square root of n is called, using the pseudonym of its discoverer, the student's t-distribution, or simply the t-distribution. Notice here that we have distinguished the variable capital T from the name of the distribution it follows, which involves a lowercase t. The confidence interval formula when sigma is known is given at the top, in contrast to the formula obtained when sigma is unknown, shown at the bottom. These two expressions have resulted from the same derivation process, but because different variables are considered in each case, the z percentile at the top is replaced by a t percentile at the bottom, and sigma is replaced by s. The upshot of this is that a different table than the z table will have to be consulted when sigma is unknown. Also, in looking closely at the formula, note that the only item needing further explanation is the percentage point of t, including its subscripts. Before computing any confidence intervals involving t, we'll discuss the t-distribution, explaining the percentile and subscripts just shown, and the use of the t-tables. To understand how to determine the percentile from the student's t-distribution, let's first compare the shape of the t-distribution to that of the z-distribution. Like the z-distribution, the t has a bell-shaped appearance and is symmetric around 0. However, in general, the t-curve is somewhat more peaked than the z and contains more area in its tails. Another major difference between the t-distribution and the z-distribution is that, in fact, there are many different types of t-distributions, yet there is only one z-distribution. In fact, there is an infinite number of t-curves, 3 of which are pictured here together with the z-curve. In order to distinguish one t-distribution from another, we must identify a quantity called the degrees of freedom, or df, of the distribution. The df is simply some positive whole number from 1 on up that identifies a particular t-curve. For example, when the degrees of freedom is 2, the t-distribution will have a different curve than when the degrees of freedom is 18. Now, in order to use the t-distribution to determine confidence limits or even to test hypotheses, as will be discussed in a separate presentation, we must determine percentiles of the t-distribution. As shown here, recall that the percentile x sub p of the distribution of any variable x is that value of x below which the area under the distribution curve is p. That is, the proportion of the population of values of the variable that lie below x sub p is p. For example, the 95th percentile of the t-distribution with 18 degrees of freedom is that value of the variable below which the area under the distribution curve is 0.95, or in other words, 95% of the values of the t-distribution with 18 degrees of freedom lie below the 95th percentile. Since notationally speaking, we need to identify both the degrees of freedom and the percent in order to specify the percentile, we generally use 2 subscripts to identify the percentile. Thus, in this example, the percentile is denoted as t sub 18.95, where 18 denotes the degrees of freedom and 0.95 denotes the proportion or percent. As another example, the 99th percentile of the t-distribution with 2 degrees of freedom would be denoted by t sub 2.99, and the area under the curve below this point is 0.99 as pictured. Now, recalling the formula for the confidence interval for mu when sigma is unknown, the t percentile in the formula had the subscripts n-1 and 1 minus alpha over 2. Thus, this percentage point has degrees of freedom equal to n-1, where n is the sample size, and the area under the distribution curve below this percentage point is 1 minus alpha over 2. Before computing these subscripts, let's review alpha and 1 minus alpha over 2. To find alpha, recall as shown in the upper left corner that the value of alpha is obtained from the general expression for the confidence level, namely 100 times 1 minus alpha. Thus, for a specified confidence level like 95%, as shown in the center, we set 100 1 minus alpha equal to 95 and solve for alpha, obtaining alpha equal to 0.05. In the lower right, alpha is illustrated as the combined area in both tails of the distribution and 1/2 alpha in each tail. Recall also that the percentile we seek in this case, shown again in the top diagram, can also be described by consulting the middle percent points of the distribution curve shown at the bottom. Looking at this bottom curve, you can see that the two areas, alpha over 2 and 1 minus alpha, added together will be equivalent to the entire green area at the top. To illustrate the computation of the subscripts of a t percentile, suppose, as with the CMI data, n is 25 and we want a 95% interval. Then the first subscript is 1 less than the sample size, or 24. The second subscript, 1 minus alpha over 2, is solved by setting 100 times 1 minus alpha equal to 95, and then using algebra to get an alpha of 0.05, alpha over 2 of 0.025, and 1 minus alpha over 2 of 0.975. The t percentile thus has subscripts 24 and 0.975, which are the two values to be looked up in the t-table. Repeating the figure showing the percentile at the left here, the notation t sub 24, 0.975 identifies that point or value of the t distribution with 24 degrees of freedom below which the proportion of all possible t values is 0.975. The table of percentiles of that distribution will now be used to look up this point. The subscripts of t provide the necessary information. Will now illustrate use of the t-table. The t percentile table you see here is in a form similar to that provided in the appendix of your viewing study guide. This appendix may be used to work the practice exercises and post-test also provided in the guide. The first column of the table gives the various values of the degrees of freedom ranging from 1 to infinity, and the first row identifies percentiles ranging from 0.60 to 0.9995. The numbers within the body of the table give specific percentile values for given degrees of freedom and percentiles. To use this table to find the 97.5 percentile of t with 24 degrees of freedom, proceed down the degrees of freedom column at the left until 24 is located, and then proceed across until the column headed by t sub 0.975 is found. The number corresponding to the intersection of 24 degrees of freedom and t sub 0.975 turns out to be 2.0639, which is the percentile we seek in the example just discussed. Thus, as the figure represents, 2.0639 is the 97.5 percentile of t with 24 degrees of freedom that we've obtained from our table. Notice that 97.5% of the area under the t-curve is below 2.0639 and 2.5% of the area is above this point. To further illustrate the use of the t-table, suppose we wish to determine the 90th percentile of the t-distribution with 200 degrees of freedom, that is t sub 200, 0.90. Using the t-tables, we would find this number as the intersection of the row with 200 degrees of freedom and the column for t sub 0.90. The value obtained is 1.2858 and is illustrated on the graph of the distribution at the bottom left. Now, before returning to the confidence interval problem we began with, let's look at the t-table to observe one other important fact about the relationship between the t-distribution and the z-distribution. Suppose we wish to determine the 0.975 percentile of the t-distribution with infinity degrees of freedom. It turns out that the 97.5 percentile of t with infinity degrees of freedom is 1.96. This value is probably familiar to you as the same value as the 97.5 percentile on the standard normal or z-distribution. That is, the area below 1.96 for the z-distribution is always 0.975 and the area above 1.96 is always 0.025. In fact, it turns out that any percentile of the t-distribution with infinity degrees of freedom is the same as the corresponding percentile of the z-distribution. Or in other words, the z-distribution is equivalent to the t-distribution with infinity degrees of freedom. Thus, as indicated here, the 95th, 97.5, and 99th percentiles of t with infinity degrees of freedom give the same values as the respective percentiles of the z-distribution. So as the degrees of freedom increases, the t-distribution approximates the z-curve. And since the degrees of freedom needed for our confidence interval is given by the sample size minus 1, we can now see that if the sample size is large, z is a good approximation of t. That is, for large n, we can use either the t-tables or the z-tables to get roughly the same answer. Now let's return to our earlier confidence interval problem using health status data as measured by the CMI score. We will apply the t-distribution and its tables to come up with an estimate of the population mean when the population standard deviation sigma is unknown. For the CMI example, our question concerned finding a 95% confidence interval for the mean CMI score of the population of heads of households in a certain community. Recall for this problem the basic data, which is given in the upper right corner. The sample size is 25, the sample mean x-bar is 20.84, and the sample standard deviation is 17.53. Recall also that this time we are using S and not assuming we know the true standard deviation of the population. To illustrate how to compute the desired 95% confidence interval, we repeat at the top left the basic data. The general confidence interval formula for mu and sigma unknown is then shown below this information. We first find the value of the multiplier, t sub n minus 1, 1 minus alpha over 2. Since n is 25, our first subscript is n minus 1 equal 24. To compute the second subscript, 1 minus alpha over 2, we must first set 100 times 1 minus alpha equal to 95, and then work algebraically as shown to obtain 1 minus alpha over 2 equal 0.975. Thus we need to get t sub 24, 0.975, the 97.5% point of the t-distribution with 24 degrees of freedom. We have previously found this value from the table to be 2.0639. With the multiplier or percentile of t now determined to be 2.0639, substituted into the general formula at the top, we can further substitute the other values to obtain our confidence interval. Using x bar equal to 20.84, s equals 17.53, and n equal 25. Thus we have 20.84 plus or minus 2.0639 times 17.53 divided by the square root of 25, which simplifies to 20.84 plus or minus 7.23, which gives 95% confidence limits of 13.61 and 28.07. Thus, the 95% confidence interval for mu, assuming unknown sigma, is given by the range of numbers between 13.61 and 28.07. The population mean might in fact lie outside this interval, but because of the procedure used to obtain the interval, there is only 5% chance of this. Here we compare the 95% interval we have just obtained as shown at the top with the 95% interval we previously computed assuming sigma was known and equal to 16. We can see that these two intervals are quite similar, even though the top interval is somewhat wider. The bottom interval, in fact, would be appropriate only if it were really true that sigma was equal to 16. If this choice had been based on previous studies of similar populations, it would seem highly unlikely that the population being studied would give exactly this value, since it is a different population. And if the true value of sigma was very different from the value of sigma chosen, the error in the resulting confidence interval could be substantial. We are just about ready to review our confidence interval computation by way of a second example. However, before doing this, we'll review the distinctions about when to use the z and t distributions to compute confidence intervals. In any given confidence interval problem involving a single mean mu, we will have to decide whether to use z or t. First, recall the use of the confidence interval formula for sigma known. Specifically, if the sample size n is large, say 25 or more, and sigma is a specified known value, the appropriate confidence interval formula involves the z distribution and is given by x bar plus or minus z sub 1 minus alpha over 2 times sigma over the square root of n. This formula is also appropriate when sigma is known but n is small, provided that the variable x is approximately normally distributed. In contrast, we show below the confidence interval formula for sigma unknown. More specifically, if n is large, again say 25 or more, and sigma is unknown, then the appropriate confidence interval formula involves the t distribution and is given by x bar plus or minus t sub n minus 1 comma 1 minus alpha over 2 times s over the square root of n. This formula is also appropriate when sigma is unknown but n is small, provided that the variable x is approximately normally distributed. Finally, note especially that if sigma is unknown and n is reasonably large, then although the appropriate formula conceptually is the one which uses the t distribution shown at the bottom, practically speaking, a very close approximation can be obtained using the z-tables instead, with the formula x bar plus or minus z sub 1 minus alpha over 2 s over the square root of n. Note that the t-tables we have provided do not provide percentiles for degrees of freedom larger than 200, and that any such percentiles that are desired are quite close to those of the z distribution, which corresponds to a t with infinity degrees of freedom. The second example for which we will compute a confidence interval involves political tolerance. Suppose a questionnaire was developed to determine political tolerance scores for faculty members. The score obtained for any individual was some number between 1 and 10, with a higher score indicating greater tolerance. The questionnaire is administered to a random sample of 9 professors at the university, and the data results in a mean score of 4.10 with a standard deviation of 1.98. Based on these results, find a 99% confidence interval for the mean score of professors at the university. To solve this problem, we first write again at the top the key information needed for obtaining the desired 99% confidence interval. Notice that the sample size n is 9, which is quite small and considerably less than 25. Notice also that no information is given about the population standard deviation sigma, so sigma is unknown. Based on n being small and sigma being unknown, the only possible choice for a confidence interval formula is the one we have been discussing in this presentation involving the t distribution, given by x bar plus or minus t sub n minus 1 comma 1 minus alpha over 2 times s over the square root of n. However, since n is under 25, before we can use this confidence interval formula, we must ask the question, is the distribution of x, the political tolerance score, normal? We cannot really answer this question without looking at the individual data points and perhaps even carrying out an additional analysis on them, or considering other studies where political tolerance was measured. For this discussion, we will therefore assume that political tolerance is normally distributed and proceed to compute our interval. Nevertheless, if it is not normal, then this procedure and its results are invalid, and we will need to consult a statistician to consider another approach. To obtain a 99% confidence interval for mu, we again repeat the information at the top and the general formula below it. Here we find the multiplier t sub n minus 1, comma 1 minus alpha over 2 by first finding its subscripts. Since n equals 9, our first subscript is n minus 1 equals 8. Further, since our confidence level is 99, we find our second subscript by setting 100 times 1 minus alpha equal 99, and then working algebraically to obtain 1 minus alpha equal 0.99, alpha equal to 0.01, alpha over 2 equal 0.005, and 1 minus alpha over 2 equal 0.995. Thus we need to look up t sub 8, comma 0.995, the 99.5% point of the t-distribution with 8 degrees of freedom. Using the tables of the t-distribution, we find this value to be 3.355. At the top, we have substituted the multiplier, the t percentile, 3.355, into our confidence interval formula. We now substitute the remaining data into this formula to obtain the expression 4.10 plus or minus 3.355 times 1.98 divided by the square root of 9, which in turn simplifies to 4.10 plus or minus 2.21, which gives 99% confidence limits of 1.89 and 6.31. Thus, the 99% confidence interval for the mean tolerance score of professors based on a sample size of 9 and assuming that the scores are normally distributed is given by the interval between 1.89 and 6.31. We are thus 99% confident that the mean score for professors at the university is somewhere between these two values, although there is a 1% chance that the mean may lie outside this range. Notice in this example that the resulting interval is quite wide when considering that the scale used to measure tolerance ranges from 1 to 10. This is primarily a result of the small sample size. Thus, our 99% interval in this case does not help much in pinpointing the true mean tolerance score. This concludes this presentation. We suggest that you work the practice problems in the viewing study guide that accompanies this program and check your answers. Then work through the test and again check your answers. You will then be ready to go on to the next topic, which is testing hypotheses for mu when the variance is unknown.